Hello and welcome back to Data Analysis and Visualization. I'm Javita Christie, and in this video, I'm going to talk about linear regression. So let's begin. First of all, what is a linear regression? Linear regression is a method for modeling the relationships between a dependent variable and one or several independent variables in order to discover and quantify the strengths of important correlations between them. So in linear regression, we will be dealing with two variables. One would be an independent variable, and the second variable would be dependent on that other variable. And of course, there are linear regressions that you can apply to several variables where that could be one dependent variable, but that variable depends on many independent variables. So the one that we are discussing right now, and the one for which I'm going to show you a program later, is going to be a one dependent variable linear regression. Now, what we do in a linear regression is we try to find if those two variables are correlated or not, whether they are actually dependent, whether that one dependent variable is actually dependent on the independent one or not. And if it is dependent, then how strong is that correlation? So that's what we are going to discuss in this video. First, we'll begin with a simple linear regression. So simple linear regression is a mathematical modeling tool that you can use to predict the values of a dependent variable, which is denoted by dv, and based on a single independent variable denoted by iv, and the linear relationship you've established between the two. So linear regression, or simple linear regression, that we are discussing here is all about finding out how one dependent variable, that is dv, is related to another independent variable iv, and finding the linear relationship between them and trying to find how strong that relationship is. So linear relationship would basically look like a line, a straight line on the graph. So that's what a linear relationship is. You'll see some examples. So right here is one of the examples, and you can see that there's a line that goes straight up, and this line is associated with the equation given right up there, which is y is equal to 3x plus 5. So this is a simple linear regression. This is the type of line that you want to create, you would want to create if you tried to apply all the calculations of linear regression on your data. So mathematically, linear regressions or relationships are expressed by a straight line. As you can see in the graph, the line does not necessarily have to be something that goes upwards. It could be coming downwards. It could be a flat line too. So it depends on the type of data that you have. And the equation that describes a linear regression is of this form. It is y is equal to ax plus b. And you might also find this as y is equal to mx plus c, or some other form of equation for linear regression, depending on which book you're referring to. So, but that doesn't matter. A and b are just variables, and you can call them whatever you like. Usually they are called a and b. Sometimes they are also called m and c. In this equation, the elements are as follows. We have y, which is the dependent variable, dv. We have x, which is the independent variable. So remember that you are trying to establish the fact that there is a relationship between x and y, and it is a linear relationship. So that's what you want to show with your mathematical model. And a represents the slope of the regression line, how steep the regression line is. So the slope essentially means when you see the line and you see that it is slanted, that means there is some slope. If you see the line which is completely a constant line, flat line, it has no slope. So A represents the gravity of that slope of the regression line. And the b is the y-intercept. So y is equal to ax plus b. Y is the dependent variable, x is the independent variable. A represents the slope of the regression line or linear regression line, and b describes the y-intercept. Now, what is the y-intercept? It is the point on a plot where the graph of a function intersects with the y-axis and x is equal to 0. This value tells you the value of the dependent variable y when the value of the independent variable x is 0. So I think that's pretty clear that whenever you put the value of x as 0 and you've got the values of y and a, then whatever value is present for y when x is 0, that value would tell you the value of b. So b is the y-intercept. It intersects the graph in the y-axis when x is equal to 0. So that's what b is. And now you know what the equation is all about. So let's proceed further and see how you can create your own regression line. Now, if you have some data on a real world phenomenon and you pair this data as two variables in a linear relationship, you're not saying that one variable necessarily causes the other. Okay, you're not trying to, when you have some real world data, you're not trying to say that this variable is causing the other variable to happen. Okay, that's not what you're saying. What you're saying is that using a linear relationship, you're showing that when one value goes up, the other also increases or decreases proportionally. So you just want to show that one variable depends for its value on another variable. So if you see that one value is going up, then you might also notice that the second value goes up as well. Or you might see that if one value decreases, the other increases. So if you see that type of a relationship, that is a linear relationship. It is not a causation. That means it's not that you're saying if this happens, then this will happen. So that's not what you're saying. You're just saying that if one increases, the other is also going to increase proportionately or decrease. And that is what a linear relationship is all about. Now, to illustrate the concept, imagine that you hypothesize that people earn greater salaries the older they get. So this is your hypothesis. People earn greater salaries the older they get. Now, when you're evaluating, you pair the wage variable with the age variable in order to discover and quantify the relationship between them. So in your hypothesis, there are two variables. One is the age, another one is the salary. So it's a nice way of saying age and wage since they rhyme. And you want to quantify the relationship between those two variables. You want to see if they affect each other. If increase in one might cause increase in the other or decrease in the other, okay? So now you discover that older people do generally earn higher wages than younger people, but is this relationship correlative or causative? Okay, correlative, which means you are saying that older people will earn higher wages. That would be correlative. But causative would mean that because people are older, they are earning more. So it's not that being older just automatically makes you earn more wages. So that's called causation. And we are going to see now the difference between the two. So if you consider the possibility that new graduates could start coming out of universities with technical skills and command much higher wages, and the older employees often may not have such skills, then you could understand that it would be possible for younger people to begin earning greater wages than older staff members. So this is a possibility that there is a person coming right out of college and that person knows a lot of new technologies and skills, and due to that person might be offered a job with much higher pay than an older staff member. So because of these things, you can say that this person is actually earning more, even though this person is not old. So that's why it is not a causation. Okay, just because you're old doesn't automatically mean you're going to earn more, or because you're young, you're going to earn less. So it's not a matter of causation, it's just a correlation. So we are only trying to establish correlation by linear regression, not causation. This means that age is not causing or driving wages. There is simply a correlation between age and wage, but this correlation is subject to change depending on circumstance. Now, to further illustrate the concept, imagine two variables, income in dollars and amount of overweight, how overweight a person is. So that is in LBS. You might imagine that as income rises, people eat more and consequently tend to be overweight. So this is another hypothesis that says that if a person earns more, then the person is overweight. In this case, you're imagining that the relationship between the IV and DV is positive. Okay, one increases, the other increases, one decreases, other decreases. So this is what you're imagining about this relationship. But maybe higher income people tend to have better nutrition information and can afford to purchase more healthy food, thus cultivating better health by maintaining a healthy weight. So this is a possibility that people with higher income, they have access to better nutritious food and might be actually maintaining a healthy weight. And the relationship between the IV and DV in that case would be negative. So while income increases, weight decreases. So in this equation, X is equal to amount of pounds a person is overweight and Y is equal to income in dollars. Now, as shown in this example, to test evidence for guesses you form about the world, you can use linear regression. So right now you do not know whether this relationship is linear or not, and you also do not know if a person with higher income is going to be overweight or a person with higher income is tends to maintain a healthy weight. So you do not know that right now. And so that's why you would use linear regression to quantify that, to understand that. And if you establish a statistically significant relationship between the independent variable and the dependent variable, meaning that you've established and quantified an assuredness that there is a real and significant relationship between the variables, then you have evidence that your guess is correct. Now you could make a guess either way, whether you're trying to guess that a person having more income is overweight, or you're trying to guess that a person having more income is of healthy weight. So either way, if you want to find evidence to which of your guesses is correct, then you could perform a linear regression and use the mathematical model of linear regression. Now, if you do not find such a statistically significant relationship, then it provides you with an evidence that your guess is wrong, and that the income of a person and the person being overweight, they do not have any relationship at all, and they are not dependent on each other. Now, how do you create a fitted linear regression line? So imagine that there is a researcher that has a data set on a group of human subjects. And this data set contains values for protein concentrations and for the number of cell mutations observed among the human subjects. Okay, so two things. One is protein concentrations, and secondly, cell mutations observed among these human subjects. Each person's record in statistical terms is an observation, and each observation has a measure for the protein concentration and for the number of cell mutations. So an observation is simply one person's record, and that person's record contains protein concentration and number of cell mutations. Two things, two variables. Okay. Now the researcher might select the level of protein concentration as the independent variable and number of mutations as her dependent variable or DV. And then try to fit a regression line to this data, meaning she would try to find values of A and B in the equation y is equal to ax plus b that would come the closest to generating the observed DVs given the IVs in her dataset. Now, think about it that the dataset already contains the values of x and y. Y is dependent variable, which means a number of mutations. X is the independent one, which means the protein concentration, level of protein concentration. So two variables are already available. You have all the values. All you need to do is create this equation y is equal to ax plus b, where you have to find the values of a and b in such a way that for all your values of x's and y's, this line describes it perfectly, which means I would find the values of a and b in such a way that if I were to provide a value of x from my current data, then the value of y produced will be something which is actually corresponding to the value of x in my current data set. So may not be the exact value, it could be, a little bit here and there, but we want that to get as close to it as possible. Now, A and B in this context are called parameters, and A is the most important one because it defines the relationship between X and Y. Remember, it's the slope. And the regression line will not fit the data exactly, like I said, because each observation is assumed to contain another random noise variable, which is epsilon, denoted by epsilon, a Greek symbol. And thus, rather than y equal to ax plus b, the equation for every observation is going to be slightly modified and is going to be y is equal to ax plus b plus epsilon. Sorry for the epsilon that's missing right there. So there is ax plus b plus epsilon, because epsilon is that extra variable that's going to be added, which is a noise variable, because your regression line is not necessarily going to fit your data exactly. You're just trying to find an approximate one. Okay. So here epsilon, this represents the new random variable. Epsilon represents the new random variable that is added. So rather than y is equal to ax plus b, it's going to be y is equal to ax plus b plus epsilon, and that's your new random variable. Now take a look at this diagram. This is a diagram of a linear regression line. You can see it's moving upwards, so it is a positive correlation. You'll learn about that later on. So what this line represents, if you could just either zoom in or try to understand, look at it closely, then the line is actually the line that we have created to fit our data set. But the dots, the black dots that you see, those are the actual data points. So this is the line that you are representing your data set with, but the dots are the actual data. So that means there is some noise, there is some value of epsilon working here, which is causing your line to be a little bit far away from the actual data points. Obviously, because your data is so scattered around the graph, you cannot really hope to create a line that's going to go pass through all the data points. In that case, your line will never be a straight line. But you want a line that is close enough to all the data points, the closest possible. So that's what you're trying to achieve here. And that's why this is the line given. And this line has been created for the linear regression line you can see right there on top, which is y is equal to 3.47x plus 17.531. So that's the regression line for which this graph is created. Now, how is the line fitted to the data? The answer is in the random variable contained in the data. So if x is 9, and the actual value is 56, but the regression predicted the value of y to be 48.8, then the difference between 56 48.8 is 7.2, and 7.2 would be the value of epsilon. Now, fitting this regression line to the data involves finding the values of A and B such that the sum of all observations in the data set is minimized. So what you want is for all the observations in your data set to be minimized. You want it to be all the errors, total errors that are happening, random noise that is coming in should be minimum. And that way you can create your fitted regression line. That's what you want from your data. So regression is a simple yet powerful tool. And if you find evidence of a relationship, either positive or negative, between the IV and the TV, then you can use the IV to predict the value of TV, as we are going to do in our next video, where I will be showing you a program, a Python program, to perform linear regression to make predictions. So you can use statistics to make inferences or test hypotheses. Hypothesis testing is a process that is used in statistics to determine the probability of whether the hypothesis you propose is true. And noise or random noise is unexplainable variation that is present in almost all data sets. So you won't find a linear regression line that fits perfectly. It will be a little bit away from the data points. And so because there's always noise in the data. So a major assumption in performing hypothesis testing is that noise terms are symmetrically distributed. And if they are not, then that means your linear model is not appropriate for your data. So if you find that the points where the noise is happening, the dark black points that I showed you in the graph previously, if those are not symmetrically distributed, then it shows that the linear model is not fitted for your data, and you might have to use a curved line instead. Okay, that could fit all the data points on your graph. So that's what linear regression is, and I'll see you in the next video where I will show you with a program how to create a linear regression model. So see you there, and thank you for watching.